All right, let me begin. Welcome back. So let me remind you quickly, the one big thing to take away from the lecture this morning was this prescription on how to construct the effective Lagrangian and to understand the limitations of the formalism. Without that, one is prone to get some errors out of the calculation. Excuse me. What I want to tell you during this lecture is two things I want to cover. One of them is the decoupling theorem. The decoupling theorem is the formal result that justifies the expansion in inverse powers of a heavy mass. I will not derive the result here. I will give you a reference. Because there's no time and it's a technical calculation that requires the choice of a specific regularization technique. Doing it right, it's involved, so it takes time. And also, I would like to cover a little bit the role of gauge invariance in effective theories. I argued that you cannot have an effective theory that is gauge variant only, say, in one operator, because the thing propagates, and I'll review that. But there's a certain aspect of gauge invariance that I think will be interesting because it illustrates the physical content that gauge invariance provides to any given theory. Now, the actual length of this lecture, of these two topics, is, I don't think, I think I will finish slightly before the time allotted for this during this hour. So in that case, I will start with the very beginning of the next lecture, because it will give me a little bit more time. Because other lectures that have much more material, and so I might spill over or begin the next lecture at the end of this one. All right. With that, let me ask if there are any questions about the first lecture. Okay, if not, let me begin. So the decoupling theorem, and as it says here, without proof. And the idea here is that one has a theory, a full theory, with two types of fields, a light field and a heavy field. And the Lagrangian can be separated, or the action can be separated into two terms, one that involves only the light fields and it's renormalizable. And this is a heavy, I denoted as H for heavy, that involves both the light and the heavy fields. Just as for the example I covered in the morning, one can define kind of an integrated effective, and I'm going to call it effective-ish Lagrangian action for reasons that will be clear below, by integrating out the heavy guys. And this is done, again, in the same spirit as in the morning, that we will not have enough energy to produce real phi's, but we can certainly probe the virtual phi, capital Phi effects. Now, if you're interested in the proof of what I'm going to tell you, it's in the nicest proof I've seen. It's in a book by Collins, by John Collins. It's called Renormalization. It's very readable. It's in chapter 8. Okay. So the result of the calculation, of doing this integration properly, is the following. This S prime has two terms, one that are divergent, and one thing I forgot to emphasize, I'm sorry to say, the fact that SL is renormalizable is actually important. In our case, in the cases of interest that we'll do, the standard model, that is not a problem. This will be the standard model Lagrangian, which is renormalizable. This would be something else. If you like supersymmetry, this would be the supersymmetric part of the Lagrangian. It has all the superpartners in it. The fermionic superpartners, say, for example. And this could be the standard model with another doublet. So two doublet, standard model, and then all the superpartners here. And what you do is you imagine a situation where all the superpartners are heavier than the energies available to one, and one gets this S prime by integrating them out. This S prime has two terms. There's a divergent contribution, and then the finite part is what I will call the effective action. Because this is a divergent contribution, or not because, but it is unobservable, and in fact, part of the proof, and the hard part of the proof, is to show that in fact, what it does, it renormalizes the coefficients in SL. So a renormalization of SL absorbs all the divergences that are produced by integrating out the heavy fields. If you actually do the calculation, you will find that there are divergences that are proportional to positive powers of this lambda, or the heavy field mass. And you might say, well, gee, that when you do the calculation, say this is a problem. I'm finding terms that don't drop, as I said earlier today, don't drop when m is very large, but on the contrary, they increase. But those terms are not observable. They are renormalization effects that we just absorb into the coefficients of SL. And then, again, the last part of the proof is that for large lambda, the scale of the heavy fields, pi, the scale of the heavy fields, the S effective can be written as a series with in 1 over lambda with operators OA that, since I've integrated the heavy fields, are made out of only the light fields. These coefficients CA are finite. OA is a local operator in the light fields F, and in particular, all observable effects of the heavy physics disappear, decouple, from when the scale of the heavy guys goes to infinity. And this is done without any, this can be proven for basically any theory that you have, which is renormalizable. Okay, that's a kind of thing, any renormalizable theory. And the condition that SL is renormalizable in the 5 fields, and this whole thing is renormalizable for the light and heavy fields, is not one you can dispose of. If that is not true, then the theorem is not true. It's an important assumption or requirement.
So the renormalizability of SL and the whole...
What do you mean?
The normalizability of SL comes into the fact that this statement that you are writing.
Well, actually, that's what happens. Absolutely. So the comment was that the renormalizability of SL ensures this is the case. Mm-hmm. If SL is not renormalizable, what happens is the heavy, upon integrating, that is, if SL has terms, is missing terms, you just don't write them down, or for some reason, then when you integrate out the heavy guys, it will generate, that integration process will generate the terms that you're missing, and they're infinite, they're divergent, and you don't know where to absorb them. And that's why SL must be renormalizable.
There's another point, that when you find out that S prime, does not that include SL? S prime? S prime,
not necessarily. Well, what happens is, not necessarily. What happened? I'm sorry. The comment was, it disappeared. So the comment was that why do you need SL to begin with? Doesn't it generate? Is it not generated by the integration procedure? So S prime will contain SL. Indeed, it will, but the problem is the coefficients are infinite. You need to have a coefficient that you can use to eat up the infinities, and so then that's what happens.
No, my question is in particular about the last statement, that when your lambda tends to infinity, shall S effective go to SL or S effective?
No. Remember, the S effective is the finite part that results from integrating out the heavy guys. Okay. So it's not the whole thing. So the total action is S effective plus SL. Okay. So basically what it says is, in these conditions, if you assume hypothetically that all the heavy physics is infinitely heavy, then you see absolutely nothing but the light theory. It just guarantees that case. If any of the assumptions that I mentioned is violated, then the result is not true. It's not true. So, okay. So that's an important thing. Okay. Again, this is useful because it justifies the expansion to all orders. From the proof, you also find that if SH, the heavy guy, is invariant under a symmetry that involves only the light fields, then S effective inherits that symmetry. That S effective can certainly be used in doing loop calculations, but again, this is an effective theory that assumes that you have integrated out heavy modes of order lambda. If you just put a few of the terms of S effective into your loop calculations, then you're assuming tacitly that you are not able to see the heavy guys, and somehow you must restrict the formalism of doing loop calculations to energies below the scale of the new physics, because you've assumed already that you don't see it.
But just one thing. So in the loop, those heavy particles can appear, right?
Okay, so what happens is that the comment was, but in the loop the heavy particles can appear, of course. But so here's the thing: if you do a calculation with the full theory, in the heavy particles, you put the propagators, and you do the calculation, and you're done, right? Okay. If you do it with the effective theory, you're not doing that. What you're doing is the propagator, instead of being 1 over p squared minus m squared, you're expanding the propagator. And the propagator becomes 1 over m squared plus p squared over m squared plus p to the fourth over m to the fourth, blah, 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 blah. If you put them all in and sum it and then do the integration, nothing happens. But that's not what we're doing. We put one term, another term, and then you will get funny divergences that are not physical, because you've assumed that you're at energies below lambda squared. And so somehow you have to ensure that the loop calculations comply with this assumption. In practice, we just put a cutoff. But for students, you should know that's usually problematic. Putting a cutoff saying that p squared is less than lambda squared is not necessarily, can generate problems with Lorentz invariance. And so that should be done with care. There's ways of putting a cutoff using regulators like polyvilars regulators that fixes the problem, but that require, if you want a rough and dirty estimate of an effect, cutoff is fine. If you want to do a very careful calculation, then you should think about how you're going to impose a cutoff and do the renormalization. Okay. Divergent pieces that you get in doing calculations are not observable. Lambda is a physical quantity, so you're imposing a physical cutoff on the integration. And if you regularize the integration using whatever method you want, the regulator is not lambda. Yes, sir?
So the SH is in the symmetry. Is it the requirement of the proof?
It's a consequence of the proof.
Okay, consequence.
It's a consequence. So the comment was whether this is this thing about the symmetry, whether it's a requirement of the proof. The answer is no. If the SH is invariant, if that happens, then that invariance, that symmetry is inherited by the effective theory. Okay. So, for example, if you have a grand unified theory, and you segregate the standard model modes with all the other modes, then, I don't know, you have your big group is SO10 or something horrible, right? But this SO10 inside has SU2 cross U1 cross SU3. It's in there, right? So the heavy guys have this U1, SU2, SU3 symmetry of the light guys and other stuff. The other stuff doesn't go down. But because the light guys are invariant under SU2, 3, and U1, then the low energy theory you get, the effective theory you get by integrating the heavy guys, will have the standard model symmetry in it. Okay. All right. That's the decoupling theorem. It basically justifies the expansion that I roughly argued and hand-waved about earlier in the day. The other thing I want to talk about is gauge invariance. So, in all the extensions, you can do any calculation with grand unified theories, supersymmetric, anything, any concrete model that you might want extension of the standard model, you'll find that the theories have a grand or large total symmetry group, and the standard model group is embedded into it. It's part of it. It could be the same. Could be the same. Like, for example, in the minimal supersymmetric standard model, they're the same. But G thought can be larger. And as I said, from the decoupling theorem, you'll find then that the OA are invariant under GSM. Because this is a subgroup of the total group. And this is what happens if you choose particular groups. But it might be interesting to ask what happens if you decide that, well, you know, there might be something else that doesn't obey this, what I'm saying, something else, that some kind of new physics where there, you know, the OA might not be invariant under the light gauge symmetry. What would happen in that case? What would be the consequences? And, as I mentioned, and to just describe this in pictures, you add one gauge variant term, and then when you do radiative corrections, this gauge variant term gives birth to all the other gauge variant terms that you can write using the light fields. It propagates. And so you might say, okay, done. You know, like I get a non-unitary theory, I stop, so I don't include this guy because I get a result that's not physical. And that's fine. But there is an aspect of this thing about gauge invariance that came up a few years back that it's worth looking at, not necessarily because it might be really interesting in itself, but because it illustrates the physical content of gauge invariance, I think, a little bit better. And this goes under the name of the Stuckelberg trick. Stuckelberg was a well-known father of quantum field theory in the 50s and so on. And he realized the following fact that, or the following procedure that can generate a gauge invariant theory from any theory. Doesn't matter what it is. So I'm going to ask you to imagine that you have a theory, which is not a gauge theory necessarily, but could be, but let's imagine it's not necessarily a gauge theory, that has a bunch of vector bosons. These are not, in principle, gauge bosons of anything. And n can be anything, can be 0 or can be 200, I don't care. And aside from this these vector bosons, you have other fields, chi. And chi are scalars, fermions, you know, if you are really adventurous, anti-symmetric, tensor fields, anything you want, you know, something else. With a chi. And there's your Lagrangian, it depends on the W's and on chi. That's it. And there's no gauge symmetry. But what he realized is that there is a way, a procedure, for interpreting this as a gauge theory in which this expression is the version of that gauge theory in the unitary gauge. And let me tell you the story of how that happens. So what he said, what I tried to emphasize, originally, these n vector bosons are not gauge bosons, but he said, let's assume they are. So I will choose any Lie group of dimension L, which is greater than n. N is the number of these guys. Number of N guys. And this group can be anything. Can be U1 to the L, or whatever thing that has more than N guys. And they're generated, and the generators of this group I call Tn, which I choose to be anti-Hermitian and normalized in this way. Standard thing. If you don't like this anti-Hermiticity, you can choose them Hermitian, and there's an I that shows up someplace else. If you don't like this normalization, you're welcome to change, and just changes the definition of the gauge coupling costs. It's just not. First thing, then you complement the original guys, but by a bunch of non-interacting vectors, W and mu, where little n goes from n plus 1 to L. You might choose L equal to n and be done, but it might be that, I don't know, that for some reason you really like SO32. And your theory doesn't have enough W's to meet the dimension of SO32, which is 32 times 31 over 2, whatever that is. And so you add the discrepancy and you put them in here there. And you put them in, how can you make them non-interacting? It's very easy. You add to this Lagrangian terms that go like kind of the F mu nu, the field strength tensor of each one separately, W mu nu n, for n equal to from here to here, and you square F mu nu n squared, you add them all up. You want to add a mass for these guys? No problem. W and mu times m, and you sum them all up. The only thing I want is for these guys not to talk to anybody. Okay? That is, they just talk to itself. Not between themselves either, just to itself. All right. So now I have an extended Lagrangian, has non-interactive these guys and the original terms that interact, and I define a derivative operator that looks familiar. It is a covariant derivative. It has the d mu, it has the w's, and has the t. Another thing. And next comes the creative part of the proof from Stuckelberg. I can say anything. So what he did is he introduced a unitary field, U. It's an auxiliary unitary field. Oh, I'm sorry. Before I go, let me emphasize the W's will become the gauge fields of this gauge group, but the chi's do not transform at all in this construction. They are singlets under this construction. All right. He introduces an auxiliary unitary field, that is, U times U dagger is 1, in the fundamental representation of G. That is, it does transform, in contrast with the chi, this U does transform under the gauge group, and it transforms like this. This is the fundamental, how the fundamental group representation transformed. Some of you might miss a factor of I. It's not there because I've chosen the Tn to be anti-Hermitian. It's just that. This is the only, let me emphasize, the only field, aside from the W's that are the gauge fields, this is the only matter field that transforms non-trivially under G. The chi's are trivially, they don't behave, feel, if you wish, any G transformation. And the last part of the construction is to define these objects, W and mu, blah, blah, blah. This is Tn, this is a generator. This is a U dagger. This is the covariant derivative, this guy, acting on U, this, and you take the trace of it. And the last part is everywhere that you see, there are as many curly W's as there were straight W's. So you can replace, wherever you had a straight W, you can replace a curly W and put it like this. Now, because this U transforms like this, and because I've assumed the straight W's, now I reinterpreted them as gauge bosons, this object here turns out to be gauge invariant. It's a gauge invariant object. Second, if I take the unitary gauge and replace this U by 1 and look at the normalization, in the unitary gauge, U equal to 1, W, curly W, becomes the straight W, I think. So you have a gauge invariant theory, because this is now gauge invariant. This has been gauge invariant always. But you have a gauge group, you have gauge transformations, you have all the things you expect in a gauge theory. And in the unitary gauge, it reverts to your previous guy. So this process creates for you a gauge invariant theory out of any theory. It doesn't have to be gauge invariant to begin with. You just reinterpret the vector fields as gauge fields. You choose a group big enough to eat them all, and then you introduce the auxiliary field U to ensure that gauge invariant is maintained. It's auxiliary because you can, by this virtue, you can always choose a gauge where U is equal to 1. It's always can choose a gauge where U is equal to 1, so that's possible. And then in that particular gauge, in that unitary gauge, you recover your original Lagrangian. Ta-da! You might say, well, then what's the point of gauge invariant? I can take any theory and make it an invariant theory. So what's the point? Good. Okay. I'll tell you what the point is. Okay. It's true that you can take any theory, make it and invariantize it, right, in this process. But it is not all. Well, it has its problems. Let me tell you what the problems are. We'll come to that in a second. So this is, I'm just recapping what I said. Any L becomes some gauge invariant theory in the unitary gauge. So why should we require them to be gauge invariant? Before I continue, let me just note that the group G is arbitrary, as long as it's big enough to eat up all the W's you started with. But it's the same group everywhere. So if you have one operator, that's invariant under group G, and you have another operator, that's invariant under G prime, it must be that G is equal to G prime. Because you cannot choose different G's for different parts of the Lagrangian. That's really not allowed. So, for example, if your terms in the Lagrangian that have dimension less than 5 have the standard model group as the symmetry group, as the local group, then all terms would have to be standard model invariant. But the standard model has what? Has a W plus W minus Z and photon 4. But you can choose, using this thing, any group that has dimension 4 or larger, and go through the procedure, and you get some gauge invariant theory with a unitary field, and that's it. You change the thing, right? That's how it goes. There's no need to have a gauge invariant requirement, apparently, at the beginning. However, as I've been emphasizing, the matter fields are all gauge singlets. And in the standard model, that is not the case. Absolutely not the case. So because they're not gauge singlets, you get lepton universality. The electron, the muon, and the tau couple the same way to the gauge to the gauge fields, to the W's and the Z's. This would not be the case in this. This would be totally accidental within the construction that I mentioned. Because the couplings to any field, to any other field, are arbitrary. You just have to be I don't know, maintain Lorentz invariance, right? There's no reason why the electron and the muon should have the same coupling to the Z. So all these are completely accidental. The masses of the gauge fields are unrelated. So the famous relationship in the standard model that connects MWMZ to the weak mixing angle would have to be an accidental result. Okay? And so these great successes of the standard model, I mean, one of the reasons we believe the standard model, one of the big reasons, is that it predicted lepton universality. It predicted this relationship that was later observed experimentally. And so it gave rise to this understanding. But inherent in deriving this thing is the assumption that the matter fields, chi, do not transform trivially or transform non-trivially under the gauge group. And the last thing is, you notice this is a unitary field. This is not your regular field. It satisfies a constraint. U dagger U is 1. That is not something you find usually in the standard model. In fact, you don't find that type of constraint in any renormalizable theory, because such theories, those that include this type of unitary fields, are not renormalizable. Again, in this case, what that implies is that the theory becomes strongly coupled at a relatively low energy. This is not the standard model W. This is the W's, the masses of the W's that I've been talking about. Beyond this thing, this type of the energies of this sort, we cannot calculate. We just don't know how it happens. And we don't know what the theory is like. The standard model does not have this problem. The standard model works very well, as far as it's been proved at the LHC, at energies above, or even those just slightly above 3 TeV. There's no indication that the standard model has any strong interactions, aside from QCD. But QCD is asymptotically free, so at energies of this sort, you have a weakly coupled theory. There's no indication that there's any effects. This theory would fail in predictability at this type of energies. So standard model gauge invariance does have does have content. Gauge invariant does have content. It predicts relations between the couplings of the matter fields. It predicts couplings, relations between the vector boson masses. It allows weakly coupled models, which seem to be, or weakly coupled physics, which seem to be the case that we have to, that we're dealing with. That's what seems to be the case from the physics we observe. So it is true that this Zuckerberg trick is interesting, right? In that you can change any theory into a gauge invariant theory, but one should separate interesting from phenomenologically relevant. So the Zuckerberg trick is interesting, but it's not phenomenologically relevant. Gauge invariance is important. The light theory should satisfy the standard model gauge invariance, and therefore the effective theory should do that as well. And the matter fields involved, the light fields that we're dealing with, in this case, the standard model matter content, all transform non-trivially under the gauge group. Any questions? This finishes this part of the thing, and I'm about halfway down the lecture, so I have time if you have any questions. I was as obscure as that. Okay. Yes?
Can you go to the last slide?
This?
Yeah. So can you elaborate the last point?
Oh, okay, so explain this part, right? Explain this part, yeah. So what happens here is the following. You can take this guy here, How do you derive it? Let me tell you. I'm not going to derive it. I'm just going to tell you how to derive this, okay? All right. So you can look at this guy. This guy depends on what? It depends on the sky, guys. It depends on the W's that are buried in here. And it depends on you, okay, on this U field. Now, what you can do is you can write U. Let me see if I can do this here. Now oh, it has to be right here. Nope. What happens if I do this? Yeah, okay. So what I'm going to do is write out the exponential field, the U field, as an exponential. U will be e to the I something, okay? And what I'm going to look is that I something at the top. I am going to, well, it's a field. It is a Hermitian field, and I can use it to do, I can do calculations with it, okay? I'll explain it a little bit in a minute. And what I'm going to do is scattering of the fields in the exponent. I'm going to tell you about scattering the fields of the exponent. So, you know the story, right? The NASA spent $1 million developing a pen for them to use, for the Apollo people to use, to write down. Because if there's no gravity, the ink doesn't fall down, right? And $1 million, you know what the Russians used? A pencil. Okay. Okay. Does it work now? I can, okay. So going back, so I'm going to write the U field as e to the I pi. Pi. Okay. All right. And this pi is Hermitian. This ensures that U dagger U is 1. Okay? And pi is like a sum of pi n and pi n t. Oh, I'm writing too fast. That's what happened. N. Nope. T n. Okay. Like I'm having a stroke. So I'm sorry. So you have to think of this as pi n Tn, okay? All right. And these pi n's are Hermitian fields, okay? And you can ask yourself, what is the scattering cross section for pi to pi? You can do that. I mean, you can do that. There are many terms, many terms. But because this term here, this guy here, has an exponential. So let's see. Let's go through this thing a little bit. Let's say U dagger is e to the minus I pi. Then this has term, but one of the terms here is d mu u. Okay, that is, if you expand in terms of pi's, what you get is powers of pi and one derivative of pi. That's what you do from this thing. So among the many terms that show up here, you have terms that have many pi's and one guy with a derivative of pi. Okay. When you put this thing in here, you will end up with terms that have many pi's and the derivative of pi squared. You will get that from the W, curly W squared. You have those terms. Okay? And so those are vertices that involve only pi's. And you can calculate using those vertices the scattering of pi to pi. Okay? And it turns out those scattering terms increase with the center of mass energy. Okay? And so with the center of mass energy sufficiently large, the scattering cross-section will become sufficiently large to violate a unitarity limit for quantum field theory. Unitarity is lost, and you have a strongly coupled theory. Okay? Now, the reason I say you have a strongly coupled theory is like I told you, I don't calculate infinite contributions to this. As I said, there are many, many contributions to the scattering. I calculate the simplest one. It violates unitarity. And I calculate the next order one. It also violates it, and it's of the same order as the first one I calculated. And so all the terms that I calculate will be of the same order, all violating unitarity. Now, what happens, really, I don't know, because I would have to sum them all up and see what I get. But I can't. But the fact that higher and higher order terms contribute the same amount to the cross-section is a telltale signal that you have a strongly coupled theory. Okay. And that's why you do that, yeah. And I hope you appreciate the art. Other question?
Just one quick thing is that, I mean, how is there any restriction on the number of chi fields that you can associate with? There is apparently no such restriction. You can, introduce as many singlet fields as you want.
Do you mean these guys? Yeah, as many as you want. You can add as many as you want. I mean, as I said, if you have 4 gauge bosons, but you really, really like SU 73, then that has 73 squared minus 1 generators.
That is for the gauge fields, but for the chi fields.
No, they're just sitting there.
Such,
as far as gauging variant is concerned. But instead of having, for example, the neutrino and the electron be in a doublet, there's no reason for that to be the case.
Correct.
So you have an electron field and you have a neutrino field, and that's it.
Yeah.
Right?
So it can be a hidden sector kind of theory.
Yeah.
You can.
Yeah, it kind of thing. But exactly. So there's no question. Other questions? Okay, if not, let me move on to the next lecture. Okay. And it is to talk about cases where there are non-decoupling situations. Okay. Now, I'm not going to cover this in great detail because the examples of that the course envisions, neutrino physics, Higgs physics, dark matter physics, they're all decoupling situations for the cases I'm going to consider. So this will be kind of an aside. But I think it has interesting aspects that will be useful. And so what do I mean by non-decoupling situation? So the decoupling theorem, as I said, guarantees that when the scale of the heavy guys goes to infinity, all the effects of the heavy guys disappear. All observable effects of the heavy guys disappear. But there are situations of interest where you want to consider theories below some scale, but that scale doesn't decouple. That is, if you increase the scale of the heavy modes that you don't want to look at, then the effects don't go away. In fact, you know one such thing. So imagine the standard model. You had the standard model, and forget about the fermions. Okay? Standard model, gauge bosons, and the Higgs. And what I want you to imagine is a situation where the Higgs is very heavy. It's so heavy that the LHC cannot see it. Okay? So very heavy Higgs. And you ask, well, it just decouples, you just erase the Higgs. But that is not the way it works. Bad things happen if you erase the Higgs. Why? Because, think about it, the Higgs mass is composed of 2 factors. One of them is the coupling constant in the potential. Lambda, let me call it little lambda, it's coupling constant. And the other is the standard model VEV, the vacuum expectation value. Now, I want to make the Higgs very heavy, but there's 2 ways of doing this. Well, 3 ways. I can make lambda and V very large, or I can make lambda large and keep V steady, or I can keep lambda steady and make V very large. Okay, if I make any of those that has V very large, has 2 effects. Makes the Higgs very heavy, and makes the W and the Z very heavy. And since I told you that there's no fermions, you're left with photons. A very boring theory. And that's not what we're looking at. We're looking at a situation where the W and the Z can be seen, produced, and the Higgs cannot. And this was the situation at LEP. It was not, I mean, this is not such a far-fetched situation. You're too young for LEP, but trust me, people like me were alive, and we saw the actual experiment happen. It didn't have energy to produce the Higgs, but it had energy to produce W's and Z's. Okay, so how do you make the Higgs heavy? Is you make lambda heavy, little lambda heavy. This is different from the decoupling case. In the decoupling case, there was a scale, thing with dimensions, that went very large and the effects went away. In this case, you have a coupling that's becoming very large. When couplings become very large, well, some masses might increase, but the interaction strength also increases, and you end up with a strongly coupled theory. In fact, what happens in the standard model when you make the Higgs very heavy is you get a theory that has W's and Z's, and if you like the fermions, you can bring them back in. They're all in there. No Higgs, but the theory is strongly coupled in the bosonic sector, and becomes the radiative corrections become too large to manage, in the sense that first, radiative corrections are of the same size every time you do a next order, so they're all the same size, precisely at this scale. And I'm not going to go through the details of that, but the reason is exactly the same. There will be a unitary field, and that unitary field you can calculate scattering, and its scattering becomes very large, violating unitarity at scales of the order of 3 TeV. So if you make the Higgs heavier than 3 TeV, the theory becomes strongly coupled at 3 TeV. And so, so there's a difference in that in one case, the decoupling occurs because a dimensional scale is assumed to be very large, or is very large. In the other case, the decoupling occurs, or the heavy masses occur because a coupling is large, and that is different. So dimensionality counts in these considerations. So I'm going to look at such cases, not all of them, but some cases where there is no decoupling. That is, heavy masses occur, large masses, because of a large dimensionless coupling. Okay? Along the way, I'm also going to talk about the decoupling case to compare and contrast. Okay. To do that, the way I'm going to present it is to go back a little bit. And if you remember, this morning I talked about hierarchies. That is a way of ordering operators into leading, subleading, subsubleading, and so on, such that the contributions, the observable contributions of the leading ones are much larger than the subleading ones, much larger than, those are much larger than the subsubleading ones, and so on, so that eventually one group will be unobservable. The effects of the groups and beyond, one point beyond, will not be observable. And the number of operators in each groups, leading, subleading, and so on, is finite. So I'm going to do a characterization of this, of a way of imposing or describing this hierarchy that will be convenient. So this will look a little bit abstract or unmotivated. And the reason I'm not able to motivate it is that I don't have any real good reason behind it. It just works. This is something that occurred to me, and it worked. And I thought it's a good way of summarizing several different types of effective theories. And so instead of going through each one separately, I can do it all in one fell swoop. So I'm going to define a property of an operator, just a number associated with an operator, every operator, that I'm going to call the index, and I'm going to call it S. Okay. And so for an operator that has little d derivatives, and B bosons, and F fermions, and the gauge bosons are buried in here in the covariant derivatives, I'm going to define this index of the operator S that depends on a real parameter U, which is not defined at the moment, just a real number, and it has this funny thing. And here, again, I apologize. It just works. It's useful because it works. I cannot reconstruct how I came up with this, but it's a useful thing to consider. You can rewrite this ugly-looking thing into a slightly less ugly-looking thing, like this. Has two terms, which I call delta. This has no little u in it, it's just delta. This is the mass dimension of the operator minus 4, delta. And multiply, adding u minus 4 over 2 times the number of matter fields minus 2. That's B matter field, F matter field minus 2. Okay, that's the definition of it. And my job is to try to convince you that this funny and contrived formula has some uses. Okay, so I am going to use this index to say that O leads O prime. So O is more leading than O prime if the index of O is smaller than the index of O prime. So, you know, this, and later on we'll see, in fact, you can check that if you choose S to be any particular number, the number of operators that could possibly have that index is finite. And again, this is useful because it encompasses several interesting cases, and what we'll see later on when we look at the renormalization group of effective theories, it's really useful in organizing the possible renormalization group contributions to the evolution of various couplings. So here's my index. Oops, at the top here. It was just a reminder of what it was. And let me consider now 3 special cases that are, as I said, of use, of interest. One of them is when you choose this arbitrary real number to be 4. Then the index becomes this thing, which is exactly the dimension of the operator minus 4. And so when I say that I'm classifying operators according to their index, I'm really classifying them according to their dimension. And what I told you is that lower dimension operators are more leading or can have stronger effects than higher dimension operators. And that is true because higher dimension operators come with a larger number of lambdas in the denominator, and so their effects are correspondingly smaller. Then there are other cases I want to consider. One of them is when u is equal to 1. In that case, the index just becomes the number of derivatives minus 1. Just period. That's it. So it's kind of a derivative expansion. And this is interesting for a theoretical model that, as far as I know, has no useful phenomenological application, just strongly coupled supersymmetric theories. I'll give you an example tomorrow. And the last one is choosing this u equal to 2. In that case, the index becomes the number of derivatives plus half the number of fermions, minus 2. In this case, then this is an ordering of operators according to the number of derivatives and the number of fermions they possess. This is useful for low energy QCD because in low energy QCD, pions are very easy to get. Pions come for free. And so having an ordering that doesn't depend on the bosons, which are pions, is very useful. And in fact, this object here is S. This is what is used for ordering operators in low energy QCD. Low energy QCD is not a decoupling situation. This is a theory that is strongly coupled, QCD, and you're just observing it at low energies. It is interesting, and you can ask, at low energies, what do I see? Well, again, it's the same prescription. What do you see at low energies? Pions. You're done, get pions. What are the symmetries? It's a chiral symmetry, SU2 cross SU2. And then you're done. You have the pion fields, you have the symmetries, you construct all the operators that have pion fields, that obey the symmetries, and you add them all up, and you get the whole description of pion interactions at low energies. And that's low energy QCD. And the ordering, and again, there's an infinite number of operators, but they can be ordered. And the ordering is obtained by this quantity. You might ask what the fermions are. Well, low energy QCD also has baryons. They're heavy, but they're there. You can consider them. And so now you have a theory that has baryons and pions. And you ask, how can we write down all possible baryon-pion interactions at low energies? And this is a theory that does that.
Is there any special reason for these choices giving rise to these examples? Or?
You know, so the question is, how the hell did this come about? Okay, it said much more politely. And the answer is, I really don't know. I'm just telling you that there is this expression here that looks very bizarre, that if you choose u equal to 4, it allows you to order things as we do for a decoupling theory. If you choose u equal to 1, it allows you to choose an index for ordering operators as we do in strongly coupled SUSY. And if you choose u equal to 2, it unifies these things. I don't think there's any profound anything at all in it. It's just useful, kind of thing that not unifies. It encompasses all three cases. There's no physics in this. It's just a good record-keeping way. That's it. There's no physics. Don't read more than that into it. So let me stop at this moment, at this time. Tomorrow morning, I will go through each of these cases in a little bit more detail and see how they come about and how the ordering is achieved and why this ordering is of use in each of those situations. Thank you. So, yeah, I didn't ask for questions because tomorrow I'm going to give you time to do the questions. So think about it a little bit, and then you can ask as much as you want tomorrow, okay? Because there's some questions right now. Oh, I'm not going to stop. Please. I intimidated them. I'm sorry. Don't be intimidated. Ask questions. Or wait until tomorrow. That's also okay.
Okay, so then let's break for tea.
Let's break for tea and reconvene for the seminar. Thank you.